chapter 3, but we'll probably actually teach it in 3 days, because normally the first two sections are like 60 slides, and then the last 2 sections are only about 20 slides total. Okay, so we'll probably do 3.1 today, 3.2 on Tuesday, and 3.3 and 3.4 probably next Thursday. It's probably what's going to wind up breaking down, but we'll see how it goes. Okay, so today we're looking at section 3.1, and what they're going to do in that is they're going to talk about kind of basic probability stuff, identifying a sample space, identifying simple events, using the fundamental counting principle, distinguish classical probability, empirical probability, and subjective probability, determine the probability of the complement of an event, and use a tree diagram and fundamental counting principle. Okay. So basically what we're going to do is first of all talk about what a probability experiment is. It's an action or a trial through which specific results, counts, measurements, responses are obtained. In other words, like rolling a dice, drawing a card. You're going to do something and something happens. Okay, you're going to get a result. That's what a probability experiment is. The outcome is the result of that single trial. Like I rolled a dice and I got a 6. Okay, or I rolled the dice and I got a 3. The outcome is what you got when you did whatever you did. Okay? And then they call it the sample space. The sample space is the set of all possible outcomes of a probability experiment. Like in other words, if I roll a dice, what are my possible things I could get? A 1, a 2, a 3, a 4, a 5, or a 6. If I roll a dice, those are all I could get. I'm not going to get a 7 if I'm rolling a dice. I mean, yes, I know there are some dice that have 7 or 12 or 15 sides, but typically as regular dice, we're talking about a normal 6-sided dice. Okay? Or if I'm, drawing a card out of a deck, it would be everything I could possibly draw out of the deck. There's 52 cards in the deck. So it'd be all 52 of those things listed out, like the ace of clubs, the ace of spades, the ace of diamonds, the ace of whatever. And yes, you do have to know cards. I had a student from Africa a couple semesters ago. She goes, but I don't know what cards are in a deck. I don't know what to tell you guys. You got to know what cards are in a deck. You got to know dice. I mean, most people grew up playing card games, so they expect that you know those. If you don't know those,
go to Louisiana.
Well, no, don't go learn at the casino, but you're going to need to know basically like how many suits are in a deck, ace through king, those types of things. You don't have to know anything huge, but you got to know the basics.
I call them shovels and puppy feet.
Yeah. Okay. And then we have an event. An event consists of one or more outcomes and is a subset of the sample space. Okay, and we'll talk about what that is as we go on. Okay, so here we go. Here's a probability experiment. They rolled a dice. The outcome they got was a 3. The sample space is a 1, 2, 3, 4, 5, or 6, which is all the choices you could have gotten. And the event is that the dice is even. In other words, if you're looking for an even number, the 2 would be an even number, the 4 would be an even number, or the 6 would be an even number. I could say I could get an odd number. I could say I could get a number less than 3. Or I could say I could get a number more than 3. Or I could, any of those types of things would be an event. What they're going to call an event. Okay, so here we go. It says the probability experiment consists of tossing a coin and then rolling a 6-sided dice. Describe the sample space. Well, first of all, let's talk about something. They're going to talk about like independent and dependent things. When I roll the dice, is that going to affect my coin flip? No. Okay. Sometimes when we're doing probability experiments, like if we draw one card out of a deck, if we don't replace that card and we go to draw another card out of the deck, there's less cards in the deck the second time you draw. Okay? So you got to be aware of if one event is going to be affecting your second event. Now here, we're flipping a coin and we're rolling a dice. One of those is not going to affect the other. Okay? Obviously, if we're flipping a coin, we've got 2 options. We've got heads and tails. And if we're rolling a dice, we got 6 options, 1 through 6. Okay, so it says to describe the sample space. So what would the sample space look like? Well, there are 2 possible outcomes. So tossing the coin, like we said, heads or tails. And there's 6 for each of the or that's the symbol space for the dice. So what they're going to use is they're going to use a tree diagram to show you. Okay, the tree diagram would look like this. Basically, it's just they list the possible things. They said they're going to flip a coin first. When they flip the coin, we could get heads or we could get tails. Then we're going to roll the dice. So if I rolled the dice, if I flipped the coin and got a head, then I could have a heads and a 1, or I could have a heads and a 2, or I could have a heads and a 3, a heads and a 4, all the way through 6. Or I could have gotten a tails when I flipped my coin. And if I had tails, then I could have tails and 1, tails and 2, tails and 3, tails through 6. We can list the things out in a tree diagram. Typically, most of you will not have to do a tree diagram, but sometimes they want to know a tree diagram, and you should be familiar with the concept. It's not too bad. Most of the time, they really just want to know how many outcomes there are. These events did not affect the other event. In other words, they were independent, which means we had 2 outcomes out of the first thing, heads or tails. We had 6 outcomes out of the second thing. And so how many total outcomes do we have? 12. How do we get 12?
6 times 2.
2 times 6, right? 2 times 6 is 12?
Mm-hmm.
Okay, if the events are independent, that's why you've got to be making those connections. It's going to have 12 events because we had 2 possible things from the first one. We had 6 possible things from the second one. Altogether, there are 12 total outcomes we could have gotten. And they listed them all out there. Heads and 1, heads and 2, heads and 3, all the way to tails and 1, tails and 2, all those. Okay, let's talk about a simple event. A simple event is an event that consists of one single outcome. In other words, like tossing a heads and then rolling a 3. On the example that we had a second ago, if I go back to that tree diagram, heads and 3 happened how many times in my target pool down here, my sample space? It only happened 1 time. There's only one way I could get that. That's why that's considered to be a simple event, because it's an event that consists of a single outcome. There was only one outcome that was heads and 3. An event that consists of more than one outcome is not considered a simple event. Say it says tossing a heads and rolling an even number. Well, if I'm going to toss a heads and roll an even number, what things would make that true? I could have heads and 2, or heads and 4, or heads and 6. So in other words, there's 3 things that would make that true out of that pool of 12 things. Okay? Which means that would not be a simple event. You need to understand when it's a simple event versus when it's not a simple event. Simple event means there's only one, that outcome only happens once. Or there's only one thing that would make that outcome true. Okay? Whereas, like, when we had heads and 2, heads and 4, and heads and 6, there were 3 things that made that true, therefore it was not a simple event. Okay. This one says, determine whether the event is simple or not. You roll a 6-sided dice, and then the second thing you're going to do is rolling at least a 4. Okay? So let's talk about is it simple? What are my options for rolling a 6-sided dice?
6.
1 through 6, right? Mm-hmm. So I could have 1, 2, 3, 4, 5, 6. Now, when it says the second event is rolling at least a 4, okay, is what things make that true?
If it rolls a
1, 2, 3.
It could roll if it has to roll at least a 4, then it would roll a 4. It could roll a 5, or it could roll a 6. So either the first time I rolled, I could have got a 1, and the second time I rolled, I could have a 4, or I could have a 1 and a 5, or I could have a 1 and a 6. I could have, if I rolled a 2 on that first roll, then I could have a 2 and a 4, a 2 and a 5, or a 2 and a 6.
You can have 3.
I could have 3, I could have 4, I could have any of those numbers, because all of these were the first roll, and all of these would be the second roll. Basically, it doesn't really matter if we list all the things out or not. They just want to know, is it simple? Is that one simple?
No.
No, because there's more than one thing that's going to make that true. Because notice it said at least a 4. You should be able to look at this one little piece right here. If it says at least a 4, that means 4 works, 5 works, 6 works. That's already 3 different possibilities. Therefore, it's not going to be simple. on top of the fact that if you actually listed them all out, you would have 3 here, 3 here, 3 here, 3 here, 3 here, and 3 here. So that had a ton of different things that would actually work for them. Okay, so it's not simple because the second outcome has at least a 4, 5, or 6. There are 3 different things that would make that true. Okay. It starts talking about the fundamental counting principle. If one event can occur in ways and a second event can occur in n ways, the number of ways the 2 events can occur in the sequence is n times n. We said this a while ago. That's what I did a while ago when I was saying, okay, how many choices do we have for flipping a coin? And you told me 2, and we said, how many choices do you have for flipping a dice or rolling a dice? We said 6. And what do we do to the 2 and the 6? We multiply them together. That's what gave us 12 choices. That's all the fundamental counting principle is. It's telling you how many choices are down there in that pool. Okay, how many things would actually, how many outcomes there are total. That's not saying all the outcomes will be what you want, because like a while ago, we only wanted the ones that were like heads and even or something. Okay, but it'll tell you how many numbers are in the pool. Okay, and incidentally, it can be extended for any number of events. So technically, I could roll a dice, I could flip a coin, and I could draw a marble out of a sack. Okay, you know, whatever. It doesn't matter how many events. I could have 10 events, and I would just do the probability of the first one times the probability of the second times the third times the fourth times however many events I have. Okay, so we could link it for any number of streamed events. Okay, so let's look at this one. It says we're purchasing a new car. The possible manufacturers, car sizes, and colors are listed. The manufacturers that we're going to consider are Ford, General Motors, and Honda. The car size that we're going to look at is compact or mid-size, and the colors we're going to look at are white, red, black, or green. How many ways can you select one manufacturer, one car size, one color? And then they're going to use a tree diagram. Okay? Before we even go to the tree diagram, how many choices are we going to have total? How many choices do we have for the manufacturer?
3.
3. How many for the car size? 2. So 3 times 2, that's 6. And then how many colors are we choosing?
4.
4. So we have 6 times 4, which makes 24. So if we list out all the things in our tree, we should have 24 things listed out there. Okay, so let's look and see what they did. Here we go. Here's their, first of all, we do have 24 things listed. That's what we said. Here's the tree diagram. First thing they did was pick a manufacturer. So they did either Ford or General Motors or Honda. Now, once they chose Ford, then they had to either choose compact or mid-size, or if they chose General Motors, then they had to go compact or mid-size, or if they chose Honda, they had to go compact or mid-size. And then once they chose the manufacturer and the car size, then they had to go down here and choose colors. So I could have a Ford compact that's white, I could have a Ford compact that's red, I could have a Ford compact that was, I think it was black, and I could have a Ford compact that was green. Okay? And then I could go over here and I could have a Ford midsize that's white, or I could have a Ford midsize that's red, or I could have a Ford midsize that's black. You get the idea. Okay? It's a way of listing out all those different possibilities. They had to choose a manufacturer, then they chose a size, and then they chose the color. And they can list it all out in a tree diagram. The main thing they want to know is how many combinations are there? How many choices are there in the pool? We had 24 choices. You do sometimes, they do make you in some of the homework, go through and do the tree diagram. Okay, so, or at least pick out the tree diagram. So you need to be at least comfortable with the idea of it. Okay, but again, nothing in this chapter is actually hard. Chapter 3 is a pretty easy chapter, guys. Okay, so classical or theoretical probability, that's what's next. It says each outcome in the sample space is equally likely. In other words, if I roll a dice, and it's a fair dice, not a loaded dice, if I roll a fair dice, I have the same chance of getting a 1 as I do a 2, as I do a 3, as I do a 4, all the way up. Okay? Or if I flip a coin, I mean, technically, you've heard of like a 2-headed coin or whatever, that's a novelty. But if it's a fair coin, then I have the same chance of getting heads and the same chance of getting tails. Okay? So, theoretical probability, classical probability, everything's likely the same amount. Okay, and the way they say that is they say the number of outcomes in the event and the number of outcomes in the sample space. And we'll look at some examples in just a second. Okay. So here we go. It says you roll a 6-sided dice, find the probability of each event. What's the probability I'm going to roll a 3? How many 3s are on a dice?
One. It's one in
One
six.
out of how many choices?
6.
6, so 1 out of 6. What's the probability of rolling a 7?
0.
Probability of rolling a 7 is 0. There aren't any 7s on a dice. Okay, 7's not on that dice. And then rolling a number less than 5.
4 and 6.
Rolling a number less than 5, that means a 1, a 2, a 3, or a 4. So that's 4 out of 6. So 4 out of 6, and they would probably reduce that to 2/3. They'll go ahead and reduce their fraction, typically. So that's what they're talking about here. So again, our sample space is the numbers 1 through 6. The probability of getting a 3 was 1/6, and they went ahead and approximated that as a decimal at 0.16. Right, that means you have about a 16% chance of rolling, actually about a 17% chance of rolling a 3 on the dice. Incidentally, you have the same chance of rolling a 4 or a 5 or a 6 or whatever, but okay. Probability of rolling a 7 is 0, just like you guys told me a while ago, because there aren't any 7s on the dice. Probability of rolling a number less than 5, we said the number 1, 2, 3, and 4, all those numbers worked. There were 6 choices total, and then they went ahead, it is actually 2/3 if you reduced your fraction, or they just went ahead and just went to the decimal and said 0.667, okay, which is 2/3. Okay, questions so far, guys? Again, most of you probably like this. This is a lot easier than remembering all the stuff on the calculator and going back and forth. Okay. The next thing they're going to talk about is empirical probability. In other words, we just looked at classical or theoretical. This is empirical or statistical. Yeah. And if they're going to want you to be able to classify as in classical or statistical or whatever. They're going to want you to be able to classify events or probabilities. Okay, so empirical or statistical probability is based on observations obtained from probability experiments. So it's like the relative frequency of an event. The way they're going to compute that is the frequency of the event, F, and we've talked about that before in those charts and those tables we've done, divided by the total frequency. In other words, divided by the total number. Okay, so here's kind of an example of it. It says a company is conducting a telephone survey of randomly selected individuals to get their overall impressions of the past decade. So far, 1,504 people have been surveyed. What's the probability that the next person surveyed has a positive overall impression?
376.
So what they're going to do is they're going to look at the number of people that had positive, which in this case is 406, out of how many people have been surveyed? 1,504. They tell you that the sum of the frequencies added up to 1,504. So we're going to do 406 divided by 1,504. Just like if you had a dice, we'd do 1 divided by 6. Same thing. So we're going to do 406 divided by 1,504. And I don't know why they actually went down and they have a mistake on their PowerPoint. Like, notice at the bottom here it says the sum is 1,504 here. If you actually look at their next slide, this should be 1,504. They have a mistake on their PowerPoint. Because when they actually go to compute it, they're dividing by 1,504, which is what it should be. Okay, it is 406 divided by 1,504, which is approximately 27%. But they do actually have a mistake on their PowerPoint. You would not divide by 320. I don't know where that number came from. But that is a definite mistake on the PowerPoint. Okay. Let's see. The law of large numbers. Let's talk about that. As the experiment is repeated over and over, the empirical probability of the event approaches the theoretical or actual probability of the event. Okay, so here's what this actually is meaning. What they're saying is that if you do an experiment, say I flip a coin twice. Okay, if I flip a coin twice, it's possible I could get 2 heads in a row. Okay, chances of that are fairly good at happening. Now, when we say what's the probability of getting a head, most of us would tell you it's 50%. It's about half. But if I'm only doing it, flipping a coin twice, it's possible that I could get 100% heads. But if I'm going to flip a coin 10,000 times, I'm not going to have 100% heads if I'm flipping it 10,000 times. In other words, if I do that experiment enough times, I'm going to get closer to that 50%, which is what I expect. That's what this is saying. It's saying that if we do this experiment a large number of times, the theoretical probability, in other words, what we expect to get, will be truer to what we should get. In other words, we expect coins to be 50% each way. If I do flip the coin enough times, it's going to be really close to 50%. But if I only do it like twice, I may luck out to 2 heads or 2 tails. And so my results wouldn't be very good if I only do it once or twice. But if I do it a large amount of times, it's going to be a lot more accurate. That's what the little chart here is showing. Like they flipped a coin here, and they had a whole lot of, this is heads, like 0.8, like 75% were heads when they first started. But as they kind of went down and they did the experiment 150 times, they got closer to 50%. Okay, that's what they were saying, is they flipped it a lot.
Long.
Okay. Okay, let's talk about this. It talks about subjective probability. It says intuition, educated guesses, and estimates. We do this a lot. In other words, a doctor may feel that a patient has a 90% chance of recovery. That would be an example. In other words, we're trusting the doctor. We ask the doctor, what are my chances here? When you're diagnosed, or you have this, or you have that. I mean, the doctor can't say, well, you have an 82.7% chance. I mean, they don't know. They're just making an educated guess of what they've seen, okay? That's not an actual numeric value, because everybody's different. Everybody reacts to medication differently. Every person's different. They're just giving you their best educated guess. Okay, that's subjective probability. Okay, so we've talked about classical, we've talked about empirical, and we've talked about suggestive probability. Now, they're going to want you to be able to classify between the three. It says that the probability that you will get the flu this year is about 0.1, so about a 10% chance of getting the flu this year. So do we think that's classical, do we think that's empirical, or do we think that's just an educated guess?
Educated guess.
It's probably just an educated guess, isn't it? I mean, no one knows exactly how many people are going to get the flu this year. I mean, depends on which strand they did, which strands were in the flu shot, whatever. I mean, no one knows for sure, but that's going to be subjective. It's most likely an educated guess. If you look at this one, it says the probability that a voter chosen at random will be younger than 35 years old is 0.3. Okay. Well, if I'm doing that one, that's going to be empirical, because that's probably based on a survey. In other words, they've already surveyed a whole bunch of other people, and those people were running kind of like that table of values we looked at a minute ago with the 1,504. Okay, this is kind of that same situation here. They would have to estimate, what was the positive or what was whatever. And so it's basically just on a survey. They would have to base it on something. It's not an educated guess. Okay, I mean, they actually have a physical number, but they would have to base it on something. And then the last one says the probability of winning a 1,000-ticket raffle with one winning ticket is 1 over 1,000. And that's just straight classic probability. In other words, what's the chance of getting a 6 on the dice? There's only one winning ticket in the lottery, so that would be classical probability. Okay, they're going to want you to be able to classify between the two. Normally, the educated guess ones are easy to figure out, and the classic probability are easy, and if it's not one of those two, then it's the other one. So there's 3 cases. So if you understand when it's an educated guess, and you understand when it's classic probability, then you should be able to, if it's not one of those two, you know which one it is. Okay. Okay, so let's talk about the range of probabilities rule. It says the probability of an event E is between 0 and 1 inclusive. In other words, if you have absolute, like a while ago, when we asked us about rolling a 7 on a dice, what were the odds of rolling a 7? 0. Why was it 0? Because there wasn't a 7 on the dice. So the lowest probability we can have is 0%. The highest probability we can have is
One.
100% or 1. Okay, because 100% is 1 when you move the decimal 2 places. So basically what they're saying is our probabilities will always range between 0 and 1. 0 means I have no chance. 1 means it's absolutely going to happen. Okay, 1 means it's a sure thing. The closer it is to 1, the better my odds. The closer it is to 0, the worse my odds. Okay. Okay, or if it's like 0.5, that means I exactly have an even chance, like on that flipping that coin. I got 50% chance of heads, 50% chance of tails. Okay? And sometimes we're really good at getting a number for something, but we don't actually understand what the number means. You need to understand when your number is 1 or really close to 1, that means it's likely and it's certain. You know, depending on how close it is to 1. You need to understand if it's less than 0.5, you know, that means it's probably unlikely, or if not, absolutely impossible, like the 7. Okay. You need to understand what they kind of really actually mean. The numbers really do mean something. Okay. And then they talk about what the complement of an event is. It's the set of outcomes in the sample space that are not included in the event. In other words, they use Venn diagrams. This is a Venn diagram for those of you that don't remember. But say, for instance, and this little markup here means complement. So this is the event. This is e-complement. This is the basically what's not in the event. For instance, if I'm rolling a dice and I want to roll an even number. If I want to roll an even number, the number 2, the number 4, and the number 6 are all in my event. If the number 2, 4, and 6 are all in here, what would not be considered an even number that's on the dice?
1, 3, 5.
1, 3, and 5 would be the complement. 1, 3, and 5 is what doesn't make the event true. In other words, if I want an even, then the complement are the odds. Or if I want a number greater than 4, then the complement is the numbers less than 4. Okay, it's the opposite of whatever we're saying. And they denoted E prime, or that E with the little markup there. That's what that means. And if I add up all the event things plus all the non-event things, then I'm going to have everything. Like a while ago we talked about evens. We had 2, 4, and 6 here. We had 1, 3, and 5 here. And so if we had all those things together, we had 50% chance of here because 50% were even. We have 50% out here because 50% were odd. And 50% plus 50% makes 100%, which is 1. Okay, that's what we're saying. Okay, likewise, if I know what the probability of one of them is, I can figure out the other because I can subtract it from 1. Like if I know I have a 30% chance of this happening, then that means if 30% chance if I have 30% chance of this happening, that means I have a 70% chance of this not happening. Okay? In other words, they add up to 1, right? If they add up to 1, if I know the odds of this, then I know the odds of that. Or if I know the odds of this, I know the odds of that. I subtract from 1. Because if I have, again, if I know this is 60% likely, that means this is 40% likely. Or if I know that this is 30% likely, then that means this is 70% likely. In other words, they have to add up to 1. Okay, and that's what all that notation was saying. Okay, let's look at this. It says you survey a sample of 1,000 employees at a company and you record the age of each. What's the probability of randomly choosing an employee who's not between 25 and 34? Okay, so here's the range that's between 25 and 34. Okay, it's 366, but I want people that are not between that range. There's actually 2 ways you could do this. One way we could do it is we can add up all the people that are not between 25 and 34. So basically we'd take out 1,000 people, take away those, okay? And we would divide that total by the 1,000. That's one way we could do it. Or if we don't want to take the time and add all that stuff up, we could find the probability of this, which is the opposite of what I want, and subtract it from 1. That's how they're probably going to show it, because they just showed you all those little formulas. Okay? So what they're going to do is find the probability of this. Now remember, I don't want these people. These are the people I do not want. Okay? But they've done the probability of that was 0.366. And so what they did is once they found the probability of that, then they subtracted that from 1, which is 0.634. Okay? Again, if you didn't want to figure it that way, you could have added up all these other guys. They would have added up to 634 and divided by 1,000, and that would have also given you that answer. Sometimes there may be more than one way to do it, is my point. Okay? So realize, as long as you're getting the right answers, don't worry about it, because there may be more than one way. Also, if you're clicking on that online help, they may show you one way, and there may be another way to do it. Okay? So if they're showing you one way and I showed you something different, doesn't mean that I'm wrong or they're wrong. It just means that there may be more than one way. And depending on how you see it, one way might be easier than the other to you. Okay, let's look at this one. It says the probability experiment consists of tossing a coin and spinning the spinner shown. So they're going to flip a coin and then they're going to use the spinner. The spinner is equally likely to land on each number. In other words, it's a fair spinner. Use a tree diagram to find the probability of tossing a tail and spinning an odd number. Okay. Well, first of all,
Sorry.
if we're tossing a coin, how many choices do we have?
2.
2. Okay, so we have 2 choices for the coin. How many choices do we have on the spinner?
8.
Now, on the spinner, there's 8 choices there. Okay.
16.
So altogether, there's how many options?
16.
There's 16 choices in my pool. The question is, how many of those are going to give me what I want? It says use a tree diagram to find the probability of tossing a tail. Okay, so I only want a tail that is connected to an odd number.
It's going to be 8.
So I want a tail and a 1. That would be a tail and an odd number. I could have a tail and a 3. I could have a tail and a 5. Or I could have a tail and a, 7 if I'm not just backwards, dyslexic or something. Okay, so basically I have 4 options that would work out of 16. Because are there any other options I missed that would be tails and odd? No. So basically my chance of getting this is 4 divided by 16. So I technically don't have to do a tree diagram to do this. But they wanted it done with the tree diagram, so we're going to do it their way. So what they did is they said heads and tails. And then you could have a heads and a 1, a heads and a 2, a heads and a 3. They listed out every single one of those things. And then what did they do? They found the ones that made it true, which were tails and 1, tails and 3, tails and 5, tails and 7. And then they said, okay, 4 of them work out of the 16 total, and that's 1/4 or 25%. Okay. So you can do it with the tree diagram. On the test, I don't care if you use it with the tree diagram or not. On the test, you're just going to be able to find the probability. Okay. So you just need to be able to find the probability, whether you're using a tree diagram. If some people like the tree diagram, and I'm going to sketch that out real quick, and if you do, that's fine. Or you can just simply do what I did. If you see the pattern, and you can just write it down. I don't care. Okay, it says your college identification number consists of 8 digits. Each digit can be 0 through 9. Basically, it's like your social security number, your school ID number, all those are numbers that are randomly generated. Okay, and each digit can be repeated. So in other words, you could have like 99999, whatever for your number. Okay, so what is the probability of getting your college identification number when randomly generating 8 digits? So in other words, they're going to randomly generate digits, and you want to wind up with your exact number out of that. Okay, so here we go. Basically, all you're doing, since the numbers can be repeated, in other words, if you use a 3 once, the next number could also be 3. So basically, it says all numbers are in play every time you're drawing a number. That's really all they're telling you. Well, for the first digit, how many choices do I have?
8.
There's 10 choices, right? Because I have 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. There's 10 choices for the first number. How many choices are there for the second number? 10. How many choices are there for the third number? Okay. That's all we're doing. So basically, we're using that fundamental counting principle of theirs, and we're going to do, there's 10 choices for the first number, and 10 choices for the second number, and 10 choices for the third number, which is actually 10 to the 8th power, which is 100 million different combinations. There's 100 million different combinations of that. So what's your odds that when you get one of those numbers, it's going to exactly match your number?
1 out of 10.
1 out of 100 million. Are your odds good?
Nope.
No, your odds aren't good. You have a better shot of winning the lottery, people. Okay, so it's not real good. So you would have 1 divided by 100 million, because there's only one number that's yours, and the odds of getting your exact number when they generate it would be very, very slim. Okay, 1 out of 100 million. Okay, and that's the end of this section. Most